Okay, welcome. In our first lesson, which this stems from Module 1 of the book, even though it says Chapter 1, you just want to ignore that. This really goes with Module 1 and should be accompanied by actually going through and reading the book as well. Sometimes what you're going to find is the book will present some of the information slightly differently, and some of it will seem repetitive, but the more that you can reinforce what you're reading with what I say, the more you're going to remember, especially as you go through and do the homework. Also, a lot of times, what you're going to find is certain parts of it stick out more to you, and it may be that the book seems a little clearer on some issues than I do, and vice versa. So always be accompanying everything that we're doing here by reading the book. And in fact, it's usually better to read the book first and then go ahead and watch the slideshows and the videos as well. So in Module 1, we're going to start talking about picturing distributions with graphs. And we're going to be introduced to some of the vocabulary that goes along with basic statistics. So we're going to move to our first slide here. And the question is, what exactly is statistics? What are we studying here? Of course, you signed up and see this as a math class, and it is. We will be doing a lot of math in this class. But the other part to this is statistics is really a look at large amounts of information. And in fact, when we talk about its having its roots in mathematics, it really does. In fact, a lot of the ways that we understand the modern world and the way we make decisions, complicated decisions, is all based around mathematics. And really it's something that is a little bit newer. It hasn't been around as long, but when we say that, it's more of talking about the last 100 or so years or more, because most of the mathematics goes back thousands of years. But as our societies become more complex and large, and especially with the computer and information revolution, we have to learn we have to be able to deal with large amounts of data. So what statistics helps us do is to take that data, organize it, and extract valuable information from it. It employs areas of science as well. If you remember in some of your science classes, one of the things that you do, or what science is based around, is creating hypotheses that you go for and test. And we also do that with statistics, and in fact a lot of statistics is used in testing scientific hypotheses. It helps us establish links and or cause-effect relationships between two sets of data or two different variables. The way we've been able to prove or show that smoking and respiratory diseases kind of go hand in hand is via statistical information. Also, you see other things of obesity and genetic and heart disease. And now, especially with our knowledge about genetics, we're beginning to learn how genetics can be linked with various diseases and other things. So there's two different ways that statistics are defined. The first is we define them in terms of their descriptions. And in fact, this is going to encompass a lot of what we look at in Module 1 and 2, is descriptive statistics, which is the actual taking large sets of data, which really is just a collection of numbers, and trying to make sense of it. So these are what we would consider the hard numbers. They're really not interpretive. For example, a runners batted in average is a number that's assigned to baseball players that is a hard number. It's based on their performance, and it's not something you can really argue. Your GPA also is another example of a hard number. It's a number that's constructed from the various grades you get in various classes. And then we have inferential side of statistics. This is about the science of gathering data, analyzing it, and then making conclusions about the overall population based on the data that we've collected. And we're also going to get into that later on down the road. So we're going to start off with statistics, but let's look, with descriptive statistics, let's look at the idea of individuals and variables. Again, I mentioned that we're going to be looking at a lot of vocabulary words. Any set of data contains information about some group of individuals. Excuse me for a second. And unfortunately, I'm beginning to battle allergies here. So, any set of data contains information about groups of individuals. Individuals are, I would say, the nouns of statistics, right? They're the people, place, or things, right? They're objects described by a set of data. So they can be people, but they can also be objects or animals. And then the thing that we're trying to measure, which is the characteristic that differentiates between the individuals, is our variable. So depending on the situation, we can take a group of individuals and there may be a large amount of variables that we could measure that separate them. For example, if we look at the college's student database, that database contains a lot of variables. So the individuals would be the college students within the database, and then the data contains variables such as sex, date of birth, choice of major, and GPA. Notice that some of those variables are not necessarily numeric in nature. For example, sex, of course, would be male or female. Choice of major, again, not a real numerical measurement, but it is something that differentiates the individual, so it can be a variable that we're looking at. So let's look at the types of variables. When we're talking about the type of data that's really non-numerical in nature, we're talking about categorical data, or variables that are categorical in nature. Categorical data are sometimes referred to as qualitative data because they are measuring qualities about our population. So they generally consist of labels and descriptions of traits. Those qualities that we're measuring, qualitative data, tend to be non-numerical, but a lot of times they can actually involve numbers that are describing those non-numerical traits. A great example of that would be, sorry, I don't want to go forward there, would be, for example, if we're measuring people's living location, a zip code would be a non-numerical measurement, right? Not really a measurement, that's a wrong word, but a non-numerical variable. So it would be categorical. It involves a number. I personally, right now sitting right here, live in 98404, but about a year ago I was living in 98402. So just the differentiation between those two numbers tells you that I've moved to a different geographical location. However, those numbers are pretty random. You know, somebody sat down and divided up the map and assigned it random numbers. Now, they weren't necessarily random. There was probably a systematic way in which they were assigned, but they have no numerical meaning. In fact, all of you within the sound of my voice probably have your own unique zip code in which you live. Some of you may have the same zip code as myself or fellow members of the class. However, so if we took all of those numbers, and there's about 30 of us, and we calculated their average, would that give us any kind of information that would be useful? And if you think about that, it obviously would not. The mean or the average of those zip codes would not be really meaningful, which is a good measurement or is a good way for you to sort of weigh whether something might be categorical or within our next category, which is quantitative. So quantitative variables are those things which are counts or measurements. They involve data that not only is it numerical, but that numerical data actually has numerical meaning to it because it was a measurement or it was a count of some sort. One of the things that what I just described really is that quantitative data, quantitative variables can be manipulated with all of those different types of things we like to do with numbers, adding, multiplying, subtracting, dividing, all that kind of thing. Average is a great one to think about because if I take everybody's height and average that out, I actually get a number that has a distinct meaning to it, which is the average height of students in Math 146. So let's give a little quiz to ourselves really quickly, talking about categorical versus quantitative data. Decide in the following which one of these variables would fall into each category. Is it qualitative? Sorry, that should say categorical. But remember, qualitative is just another word that's used at times. Or is it quantitative? So, for example, the heights of members of a basketball team, would that be categorical or quantitative? And the answer there is quantitative. Height is a measurement, and in fact I just mentioned it in describing quantitative data. Flavors of ice cream at a local parlor. Well, flavors of ice cream are pretty straightforward. Those would be categorical in nature. Those are names assigned to different flavors. The jersey numbers of the Seattle Seahawks. Now here's an example of a variable that does vary from the members of the team, but is not a number that has any kind of mathematical meaning to it. So this would be an example of categorical data. Those numbers are assigned, but they are not a count or a measurement. The waiting times at a busy intersection of town. Well, that's a measurement of time, so that would fall into the quantitative category. And then the number of planes landing at SeaTac Airport. Again, that would be a measurement in terms of it's a count, and so therefore that would be a quantitative variable. Very good. So we're first going to look at what we do with data that's categorical and how we can organize it. This first section is really all about once we've gathered data and we have it, how do we organize it in a way that can display the meaning simply from a picture. There are obviously many benefits of displaying graphs of data. It gives us a picture of our data in one foul swoop. It's easier to view than looking at a bunch of numbers or a big collection of names and labels. And it gives us a snapshot of patterns without having to do a lengthy analysis of those patterns. And of course, it's visually appealing. We all like to look at graphs as opposed to large sets of numbers. And so when we talk about categorical data which is non-numerical, there's two main ways in which it is typically displayed. Number one would be a pie chart, which I'm sure you're familiar with, and the second also that you're familiar with is a bar graph. Those are the two main things we're going to look at. You can tell by this first graph that it is showing the housing of college students and what types of places that they live. And already just taking a brief look at the graph for a few seconds, you can tell the majority of students at this college live in apartments. And then the second largest group would be dorms, and then you have houses, and then sororities or fraternities. Now, how are pie charts exactly made? Now, most of the time, what we're going to be doing is analyzing pie charts and using them to make conclusions. But how exactly is it organized? The first thing that we start with, which we do for most graphs, is to create a distribution table. We're going to refer to these as frequency distribution tables. So here we have it. We have types of housing. We have our categories: apartments, dorms, houses, sororities, fraternities. And we go out and we poll. It looks like in this case we've got, looks like 49 people. I believe that's right. Yeah, 49 people. And so we pull them and we find out where they live. Okay, and then we just simply categorize them according to who lived where. Now, once we've done that, we want to calculate what the frequency is. Now, the previous column, this column over here, would really be our frequency column. When we talk about frequency, these are just the number that fell within that. When we get to the percentage part, this is generally referred to not as frequency, but as relative frequency, because relative, and whenever you see the term relative, especially in a math context, generally they're talking about percentages. So we've taken each one of these numbers, for example, 20, and we've divided 20 by 49. If you take your calculators and go 20 divided by 49, you get 0.41 approximately. And so we change that to a percent. We say, okay, 41% fell into that column. Now, why would we choose relative frequency over frequency? Well, generally, relative frequency gives us a bigger picture just in the one number itself. If you weren't looking at this table and so you had no idea how many people participated in the survey, and I just said, well, 20 of our participants lived in apartments, that doesn't really tell you anything until you know 20 out of what, right? So if 20 fell into apartments, if there were 100 students, that would be a very small percentage. It would only be 20%, right? And so what the percentage does is within one number, you get an idea out of the population, what chunk of the pie fell into that category. And with pie charts, that is literal, because we can take that percentage now, that in decimal form, multiply it by 360, which is the total number of angles for a circle, and we get 147%, or not percent, but degrees, which tells us how much of the circle is going to be made up of apartments, right? And so we get these degree measurements for each piece of the pie. Then we take those pieces and we turn it into, as you saw in the previous thing, the pie chart. Now, like I said, we're not going to be analyzing that in terms of, I'm not going to have you make a pie chart, but that is how it would be done. All right. A bar graph is also used to represent categorical or qualitative data. In a bar graph, the height of the bar is what we use to show the amount of data that's in that category. The horizontal axis, which is the x-axis, if you remember back to your x and y charts, contain our categories. Now remember, with categorical data, it's non-numerical in nature, and so where we place those categories on the x-axis is really up to us. So there is no set way to organize those bars. If they are put from lowest to highest or highest to lowest, we simply call that, we give it another name, it's called a Pareto chart. And you may see that word thrown out there, and all that is a bar graph that's been organized from highest to lowest or lowest to highest. Now the vertical axis we use as the frequency. So that is the number of data or datum that appear in that category. And the width of the bars in a bar graph is meaningless but should be uniform. Typically also we tend to, and I'll go back to here, we tend to have spaces in between our categories in a bar graph. Alright, so in creating a bar graph, we first start off with creating a distribution chart. The distribution chart lists our different categories and the frequency of each category. And then we create our bar graph. You can see this one here was done from highest to lowest. However, again, there is nothing to say that that's the way it had to be done. I think by pure coincidence, these happen to be arranged in alphabetical order, but I think I discovered that after I'd already created the chart. All right. So that concludes our first part of this at organizing data, and of course, introduction to all those different vocabulary words. Continue on now to the next presentation, where we're going to talk about how we organize quantitative data.